So we'll watch this little thing on Peregrine Falcons here. Free fall, humans versus falcons. It's kind of cool. It's about slideshow from beginning. There we go. That's where we went. Oh, you guys can't even see what I'm doing. Oh man. Parade back and forth. Screen down. Oh man, I forgot how to work this stuff completely. Okay. You'd think I'd know because I just came. We'll wait calmly. And then what we're going to do after we watch this little video is we will look at how many of you started homework 5 and realized that we haven't even covered most of that stuff yet, or the second half of it. So, right, all right. So Don's like, what? Okay, we're going to learn how we're going to throw a ball sideways, learn how those problems work, okay? Learn how long it's going to be in the air, learn how far it's going to go, and learn how fast it's going to hit the ground. Yes? What's that?
The hints were off again on homework 4.
The hints were off? Well, not all of them have hints. So.
Well, I mean, but like, we still didn't have feedback. Like, I got it wrong, I had no feedback, so I don't know what I did wrong, and I don't.
Oh, really?
Yeah.
Oh. Okay, homework 5, they're there though, I think. Yeah, I like the homework. So from now on, here's the way homework's going to work. We're going to send it to you on Friday. It'll be due the next Friday, and it's going to be those. It's going to be those student tutorial problems. That's what those STPs stand for. Those things you kind of work through. I like those because I think they kind of teach you, vice just doing the random problems in the book. Okay, so that's what, and they'll be due each Friday. Because some of you, the random way that I've done the homework so far is I'm still learning the system is kind of driving you nuts. So now, from now on, it'll be Fridays. You'll get a new assignment. It'll be due the next Friday. Okay, there. So now you can plan your life. Except I think this week, all you science majors, don't you have some tests and stuff? And they kind of, yeah. Well, that's kind of the way it goes. Like I've told people before. You know what they call people who are able to get all their homework done and then take all their tests at the same time and still do good? Doctor. All right, anyway. All right, so here we go. We'll also watch a little thing on Tiger Woods too, but that's not the one I wanted. This is the one I wanted. What's going on here? Hold on a second. Free fall, Falcons versus humans. Oh, here it is, terminal velocity. I'm sorry. Oh, right here. Boom. These are. Wait a minute, that should be getting bigger. Where's my thing to make that bigger?
I'm Boyd Maps.
What's that? Oh. Under it right here? Oh. Thank you. That was a challenge here. Okay, there. Oh, thank you, fellas.
I'm Boyd Maps.
Here's a little free fall.
Even in a sport like skydiving, there are those for whom terminal velocity is just not fast enough. Projectile is speed skydiving, what some call the fastest non-motorized sport in the world. The goal is simple.
Just get out of the plane and trying to go as fast as we possibly can in free fall.
A normal skydiver in free fall hits a top speed of around 120 miles per hour. Mark wants to go faster. And when it comes to raw speed, the Peregrine Falcon puts humans to shame. Commercial pilot Ken Franklin is determined to get a fix on the Falcon's speed. At home, Franklin raises his own Falcons. But only now does he have the bird he's been waiting for his whole career, a female called Frightful. She's the one he believes will help him unlock the secret of the Peregrine's amazing speed.
So that was the motivation for me, the dream of flight and the reality that at some point I could actually look in a falcon's eye while it's flying.
The key to Franklin's method is training his birds to follow him. To do that, he designs his own lures, small cotton bags filled with lead weights and topped with a piece of meat. Franklin heads up, releases Frightful, and at 12,000 feet, she goes into her dive.
This is very exciting. This is
After 10 seconds, she's going 120 miles an hour. Franklin releases the lure. Franklin shifts into hyperdrive, actually changing her shape during her dive. Her wings are folded back into her body, and she is transformed into a small flying teardrop. To help her handle these speeds, Frightful is also built differently than other birds. Her feathers are longer and harder, allowing her to maneuver at high speeds and pull out of steep dives. In only 43 seconds, Frightful snags the lure, pulls out of her dive at 3,000 feet, and heads home. Moments later, Franklin's chute snaps over. The verdict is in.
183 miles an hour.
And 1 week later, Frightful breaks her record, diving at an astonishing 242 miles an hour. Humans, determined to reach similar speeds, took a page from the Falcons book and designed special suits that would allow them to stay stable when skydiving.
These pants are actually big earth scoops on. The bottom half of the pants actually inflate, and it gives you the shuttlecock effect.
Mark's burly upper body is like the Falcons, the tip of a teardrop, like a shuttlecock in badminton. His air-filled pants are the feathers. The pants increase Mark's drag, but they give him much more control. Gravity does the rest, and Mark has hit top speeds of just over 300 miles an hour, thanks in part to the same techniques used by nature's fastest hunter.
Okay, now, let's go ahead and raise this up. And let's talk about, not so much the Falcon, I just found that to be kind of interesting, and that someone can get going 300 miles an hour in free fall. It's pretty amazing. Okay, let's talk about how do we do these projectile motion problems, because we've talked a lot about projectile motion, but we haven't really put together any problems yet. Okay, so here's the first one we're going to do. What we're going to do is we're going to take a ball, we're going to throw it off a 49-meter cliff. There's a method to my madness here on why I chose 49, because eventually I'm going to divide by 4.9, or 1/2 g. Okay. And I'm going to throw a ball pretty fast this way at 30 meters per second. Okay? Now, here's one idea from this. Everything we do is x components and y components. Okay. When we do projectile motion. Okay, so we got x component stuff and y component stuff. So right now, I've thrown this perfectly horizontal at 30 meters per second. So my initial velocity in the x direction is 30 meters per second. Now here's the first big idea. What's my final velocity? Yeah. In the x direction, my final velocity will be 30 meters per second. What's my initial velocity in the y direction? No, my velocity. What's my initial? That'll be my velocity in the y direction after 1 second. What's my initial velocity in the y direction? 0. Exactly. So this is just like being at the maximum height of a projectile motion problem when we go from height smallest to biggest. Oh, I forgot to finish the slideshow on chapter 3. That's all right. We'll do this problem, then we'll go through the slideshow, then we'll do the next problem. That'll work. All right. So we got y. All right. Now, what's the acceleration in the x direction?
0.
0. Because there's no change at all in its velocity, so therefore there's no acceleration. Okay. What's the acceleration here? Right, negative 9.8 meters per second squared. Now here's the big questions that we're going to ask. One is, what's the range? What's the range? That's how far it goes this way. Okay? The range will be measured out here. It's going to come down and hit right here, and this is R. Okay? What's the range? Range is pretty easy to find if we know this. Total time in the air. We want to know the total time in the air, and we want to know the magnitude of the final velocity. So in other words, we want to know what the magnitude of the final velocity is, so it'd be v naught x squared plus v final y squared. Okay? Now, those are the questions that we want to answer. And we also want to know, what's the height going to be after 1.5 seconds? Say. I've already done this problem, so I know it's in the air for at least 1.5 seconds. So I can ask that question. What's the height going to be at 1.5 seconds? All right. Projectile motion, you do most of your work over in the y component. The only time you jump to your x component is when you want to find your range, which is real easy once you know the total time it's in the air, right? If you know the total time it's in the air, then the range is a piece of cake. It's just the x velocity times the time, because that's how far it's going to go. This way, all right? So that just becomes v naught x times the total time. So when we figure out what the total time is, look at that. Now, to find the time that it's in the air, it's just like a free fall problem if I take this marker and drop it. Okay, if I take the marker and drop it, boom, it's going to hit the ground at the exact, we can figure out how long this thing will be in the air. So here's a conceptual question for you. What would happen if I shot this guy 30 meters per second sideways and I dropped a rock at exactly the same time? Which one would hit the ground first? Same time? Same time. Be the same time. Because the y velocity on him is, they're both starting out at 0, right? And the only acceleration is going down. So they're going to hit, they both hit. So if I shot one sideways, vertical, and I dropped one from the same height, boom, they're going to hit at the same time. Now, this one's going to be quite a ways down range, but it's going to hit at the same time. Yes?
Yeah, I mean, so that just the same with no matter how fast you launch a projectile without air resistance, it will just reach that point. I mean, it might be farther.
Exactly.
Direction, but it'll.
Right. Right.
I just, yeah, I was thinking about that.
Yeah, so you're getting the whole idea of escape velocity, which is really fast. Okay, so we got to get up really high and really get going fast so that we start falling so that we can't catch up with the Earth. Because basically, what you do when you orbit is you're up high enough so that if somebody, in other words, we can get high enough, if we get high enough and throw a ball fast enough, it'll come around and hit us in the back. Okay? Because it's never going to hit the ground, but it's going to go all the way around the Earth. And so that's basically what the moon's doing. All right, I'll let you think about that one for a while too. All right, so you got 30 meters per second. All right, and so it's going to hit. They're going to hit the ground at the same time, and we can figure out what the time is on this real simply. We're just going to use this guy, this little free fall formula where y equals y naught plus v naught y times t minus 1/2 gt squared. I've already factored the negative sign out of the g there. So when it hits the ground, what's my y final? Here, oh, let me put the y final here. What's y final when this thing hits the ground? It hits the ground. Yeah, what's y final? 0. Right. Okay, so this is 0. This would be 49 plus 0 times t minus 4.9 t squared. Okay, so we add the 4.9 t to both sides, t squared to both sides. This is why I chose 49 meters. Divided by the 4.9, we get t squared equals 10. Take the square root of both sides. We get plus or minus 10 square root of 10 seconds. Now, the negative 3.1 seconds, so that comes out to be plus or minus 3.16 seconds. Okay, I guess we're using 3 significant digits here. That's what I arbitrarily picked, even though I've been using just 2 up here. All right, so anyway, 3.16 seconds. Now the negative part is how long it took to get up from this imaginary place here. Really. That's your negative part. But physically, you can't go back in time. All right? So it's an irrelevant answer. So the only answer is the positive 3.1 seconds. So remember, if we take projectile motion, or if we take free fall, just the y, the t versus the altitude graph, you're going to get a nice parabola that looks like this when you're got your constant acceleration of gravity. All right. So, is in the air 3.1 seconds? Well, we answered that. That was easy. Well, that's 3.1 seconds, not 3 pounds. Okay? It's 3.16 seconds. Now, what's the range? Well, now that's going to be real easy to get because we already knew the initial velocity. So we got v naught x equals 30 meters per second times the 3.16 seconds, and that will about 94 meters, I think, right around there is what I recall. So that goes out 94 meters here. Okay? And what else did we want to know? Oh, it's final velocity. It's final velocity when it hits the ground. We've got a and its height at 1.5 seconds. So here's its height at 1.5 seconds. We'll just use this formula here. We'll say, okay, well, y equals 49 minus 1/2 of 9.8 meters per second squared times 1.5 seconds squared, and that comes out to be about 38.8 meters. In other words, I just stuck the time into this equation and figured out what the height was. Yeah.
It's like something, predicted. Like a trial and error method. Could you just, like, with the idea that gravity is 9.8 meters a second, could you go from knowing that you have the height of 49 meters, just for this case, like, say, well, the first second I'll be at 9.8 meters a second, the second I'll be at 19.
That's how fast you're going to be. That's not how far you're going to be. Okay. Now, he brought up a good point. Be careful. Okay? In other words, he was figuring out, he was going, oh, well, after 1 second I'm going to be at 9.8 meters. No. After 1 second you're going to be at 9.8 meters per second, but you're only going to be at 4.9 meters, actually. Well, it's a quadratic. It's a quadratic. So it depends on your time. It's squared. It's squared. So that's why after 1.5 seconds, almost after half the time, I've fallen a heck of a lot less than half the distance. But I'm going to pick up real fast because after 2 seconds, I'm going to be falling at 19 meters per second, 19.6 meters per second. After 3 seconds, I'm going to be hauling at almost 30 meters per second, which is really fast, which is as fast as that. And then boom, I hit.
Yeah, I was just trying to draw it out, the other day. I was like, I wonder if
No, you got to remember, acceleration is the rate of change of velocity, and the velocity is the rate of change of the distance. But if the velocity is always changing, then the distance is going to grow exponentially. Okay. All right. So now we wanted the final velocity. So here we go. Final velocity is not bad. Now we can do what you said, basically, because we know this: that the final velocity is equal to. Well, let's do it this way. Let's look at the actual acceleration. The acceleration is constant. So for the y component here, for the y component, since the acceleration is constant, we know the acceleration is negative 9.8 meters per second squared, which equals final velocity minus the initial velocity divided by the time. That's what you were doing. This right here. Okay? And so we get negative 9.8 meters per second squared times the time, which is 3.16 seconds, equals the final velocity, y. And the final velocity is negative, which makes sense to us because it's going to hit right here. Okay? It's going to hit, and it's going to have an x component of 30 meters per second. And that actually comes out to be a y component of negative 31 meters per second. Okay? So the magnitude of the final velocity then is equal to the square root of 30 squared plus 31 squared. And I have to look that up. It's basically 30 times the square root of 2, which comes out to be, I can't remember. Boom, 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 boom. I don't have it. Oh, I forgot to compute that one. It's pretty quick. All right, so that's that one. Now, let's take a look at our slides, and then we'll do one of the problems where we start from the very back and shoot all the way around. Okay, because we're going to take a quick quiz at the end of all this, which will make sense once we go through.
What does it end up being?
What? Oh, I don't know. Whatever this ends up being. 31 squared plus 30 squared. Take the square root of that. Yeah, you kind of sat for the whole movie, and I forgot to tell you the ending. It's 1861. Square root of 1861. That's when the Civil War started, by the way. 43.1 meters per second. There you go. All right, let's lower the magic screen here. We're seeing the free fall and the terminal velocity. Got one other thing for you, because this is what we're going to figure out, and we're going to see how bogus our answer is compared to with what a real world answer is. Here's a real projectile motion, and this is just about a minute long. They've got all these fancy cameras now at these things, so we can actually.
Iris can be above your head, even talk. Iris can be above your head, even talking. Not aware that you're trying to concentrate. Just wait.
Obviously, this isn't Sunday. Why is this not Sunday?
Tiger made a birdie here yesterday with a.
He's not where you're at. Exactly.
Bunker on the right-hand side. You see the club head speed, 116 miles an hour with a 3-wood. That is very impressive.
And the ball is very straight, Gary.
169 mile an hour.
Most pro golfers
Speed,
have a club speed about 100
262 yard
miles.
carry with a 3-wood. Wow. This numbers courtesy of our TrackMan
Oh, I was
technology.
yakking.
Mickelson
on.
off that unbelievable par save.
2-wood. Wow. This numbers courtesy of our TrackMan technology.
What?
Mickelson off
I
that
forgot to get the numbers.
unbelievable
What were they?
par save.
169 miles an hour, 269 yards, right? Sorry about that. Let's try that one more time.
We see the club head speed, 116 miles an hour with a 3-wood. That is very impressive.
And the ball is very straight, Gary.
169 miles an hour.
Ball speed,
And 262 yards.
262 yard carry.
Wow.
3-wood. Wow.
Okay.
This,
All right. So we're going to look at that problem. We're going to come up with, now the 169 miles an hour that they came up with was probably from the time they knew how far he hit it and the time the ball was in the air, so that was just the X component of the velocity. He actually hit it much faster. And as you'll see, when there's air resistance, golfers don't want to hit a ball at 45 degrees, which gives you your maximum distance in perfect conditions. They want to hit it a little bit more of an lower angle, okay? And so that's why we shoot things. We never shoot things at 45 degrees. We always have it a little bit lower because in the real world, it's going to blow back on you, all right? Okay. Whoa! Got the wrong thing. This is your quiz. Let's go to the lecture. All right. Now, we've already been through a lot of this stuff. All that good vector stuff. All right. Now, we've already looked at this one. So, at the very beginning, V naught y is equal to what? His y component of the velocity is, when you're throwing it, when you're standing up, what's it say?
0.
0. There we go. Okay? And notice, the Vx naught is equal to Vx at the end. Vx never changes. But Vy keeps getting bigger and bigger because gravity is what's pulling it down, and it's giving us the rate of change of the velocity. And X max here is what we know as what we call the range. Okay? All right. Now, here's hitting a golf ball. Notice, you got V. If we were given V, how would we find this Vx naught? How would we do that? What do we multiply by if we knew this angle? Cosine of that angle. Right. And how would we find Vy naught if we knew V naught and we knew this angle? What would it be multiplied by? Sine. Very good. Okay? And notice, all right, now, don't fall for this kind of trick question that says, what's the velocity? Here's his question. What's the velocity of the ball at the maximum height? What's the velocity of the ball at maximum height? Not 0. What's the velocity of the ball at the maximum height? Here's the maximum height. It's
The velocity in the x direction?
Yeah. So it's got the velocity in the x direction. What's the velocity in the y direction at the maximum height, though? 0. See, from chapter 2, when we were doing the straight up and down free fall problems, when we threw the ball straight up in the air at the maximum height, well, its velocity is 0. And we're going in two-dimensional direction. This x never changes because there's no acceleration working on it because we're neglecting air resistance. And so when it gets to the maximum height, it's still going Vx. All right? What's that? Yeah. So let's say this Vx is 30 meters per second. Vy is 40 meters per second. Then V naught would be 50 meters per second. Okay? When it gets up to here, Vy is 0 and Vx is still 30 meters per second. Okay. All right. Good. And here, if you throw it down, now it's going to be in the air less time, but the final velocity when it hits the air is going to be the same as the final velocity when it hits there. It's just going to be in the air less time here. Okay? Because remember, what goes up, so this one's going to go up, and it's going to come down at the exact same velocity at 45 degrees as this one is right here. So they follow the same trajectory. They follow parallel paths, basically, once you get to the horizontal. Okay. All right. This is an interesting slide. Oh, I forgot to call up the FET thing, where we actually shoot stuff, which I might do here in a minute. Okay. Notice something here. What about the range of the 75-degree angle and the range of the 15-degree angle? The range is the same. Which one spends more time in the air? The 75-degree shot or the 15-degree shot? The 75. How much time it spends in the air depends on the height. Okay? How much time it spends in the air depends on the height. Okay? Notice, what do you get when you add 75 and 15? 90. What do you get when you add 60 and 30? 90. So, two shots that are complementary angles of each other go the same range. They have the same range. Just the one with the higher range can say 45 and 45, which gives us our maximum range in ideal conditions. All right? But normally golfers want to hit it around the 30-degree thing because the actual flight of a golf ball kind of goes like this, and then it drops pretty quickly because they hit it so hard that it reaches a maximum velocity and then it just falls. Okay. Okay. All right. We're about, oh, there it is. Okay. I forgot. They gave you the, okay, if you're under 45 degrees with air resistance, see how it shoots a little bit further than if you shoot it at 45 degrees with air resistance. So you want to shoot a little bit under. Due to air resistance. All right. And we're not going to do relative velocity except next semester when we talk about special relative velocity. But you should know, I would be remiss if I didn't teach you a little bit about relative velocity, in that I think we talked about it before. If you're going 20 miles an hour west and somebody else is going 20 miles an hour east, the person that's going west, how fast does that person going east seem to be traveling? 40 miles an hour. Right. Okay. There you go. You've got it. You figured it out. Okay, good. Turn off. There we go. Now, let's do that last problem. Then we'll flip that thing back on for a little quiz here, and we'll be done for the evening. All right. Those slides aren't real detailed, but they kind of give the big ideas of the stuff. All right. Now, this time, we're actually going to do that Tiger Woods shot, but this time I'm going to say that he actually shot it at 169 miles an hour. And we're going to figure out how long he was in the air. We're going to figure out how long, we're going to figure out how high the shot went. We're going to figure out how far it went. And you'll have to do that on the test a week from Tuesday. I'm just going to tell you, you're going to get a problem where something's going to be shot at an angle, and you're going to figure out how far it went, how long is in the air, and what the maximum height was. And maybe answer a few other questions that go with it. All right, so first of all, let's take that 169 miles an hour, and I'm going to give you, and let's say he shot it at 30 degrees. Okay, he shot it at 30 degrees. Now, if he shot it at 60 degrees, we're in ideal conditions. It would have gone the same distance. But he shot it at 169 miles an hour at a 30-degree angle. All right, now, let's take 169 miles per 1 hour. Okay? And let's change this to meters per second. It's really not all that hard. Basically, anytime you want to change miles per hour to meters per second, multiply by 4/9 or 0.44. Works out every time. It's that simple. Because I got 1,600 meters roughly in 1 mile, so that cancels that, times in 1 hour, I have 3,600 seconds. So 16 over 36 is 4/9, it's 0.44. So I got 169 times 4/9, which comes out to be about 75.1 meters per second. All right, now, what we want to do is we want to find the range, we want to find the height, so give us maximum height, and well, what's the final velocity going to be? What's the magnitude of the final velocity going to be right here? Yes. Okay. It's going to be 75.1 meters per second or 169 miles an hour. Remember, what goes up must come down at the same speed. Okay? As long as there's no air resistance. So here we go. Let's figure out, we're going to find the range, the height. Oh, we want to find out how long it was in the air. All right. So we got our x components over here. Let's go ahead and let's just start work on this guy. X components, y components. Okay. V naught x. How am I going to find the V naught x thing? The initial velocity in the x direction, how do we find that? The sky times the cosine of the angle. 75.1 times the cosine of 30. And I actually worked these out ahead of time, believe it or not. That comes out to 65 meters per second. It's pretty quick. All right, I know I'm beating a dead horse here, but what's the final velocity in the x direction? Yeah, 65 meters. that one, right? Yeah, 65 meters per second. All right. What's that? Why isn't it 0? Okay, after it hits and stops, it'll be 0. But, yeah, right when it hits the ground. Yeah, that's what it means. Good question. Good question. Right when it hits, the proper way to ask it is, what's the final velocity when it hits the ground? Okay. All right. And what's the acceleration in the x direction? 0. Okay? And so if we find the range, that'll just be V naught x times the total time. Now we're going to find the total time first, but first let's fill in our y components, what we know about the y components. We've got V naught y, which I find that by 75.1 times the sine of 30 degrees, which the sine of 30 is basically a half. Not basically, it is a half. So this would be 37.5 meters per second. V final y. Oh, I want V final at h when it's at its maximum height. What's that going to be? When it's up here, what's the y component of the velocity right up here? 0. Okay. The time of the total flight, I don't know yet. I do know the acceleration is negative 9.8 meters per second squared. And h, I don't know. But I've got a way to figure that out. There's a couple ways to figure out h. Let's say, for sake of argument, that the total time this thing was in the air was 8 seconds. It's going to be close to 8 seconds. It's a little bit less than 8 seconds. How long would it take for it to get, this might be confusing. The total time is when it gets over here. Okay, that's the total time. Now, what do you think, if this is equal to 8 seconds, for right now we're going to put 8 seconds. So don't write that down and put it in your notes and then get all confused later on. You go back, okay. How long would it take to get here? 4, right. Remember, in ideal conditions, we force Mother Nature to like symmetry, okay, in ideal conditions. All right, so this total time would equal 4. Half. This is t at h is equal to 4 then. All right? All right, but that's not exactly the way it turned out. So let's erase that real quick. I just wanted to make a point that that's what it would be. It'd be half. All right, we can figure out this total time real easy because what is the height of this ball at the total time? What's its height? It's going to be what? 0, right? So we've got that nice little formula, that nice little quadratic, which equals this. We got y equals y naught plus v naught t in the y direction minus 1/2 gt squared. This is a wonderful little formula, okay? Because, especially now, because we can do this. We can go 0 equals, remember what I said, we do, with projectile motion, we do most of our work over here in the y component and then just throw the x component a bone once we get the total time and multiply by vx and we get the range. All right? So we get 0 plus 0 plus 37.5t.
Now what's the y?
What's that?
What's y? Just y.
What is it? That's the height. Y is going to be the height.
Is that just like a generic y equation, I mean, like for height?
Yeah.
That's just like, that's the mainstay.
Yep. This is the expression for finding the height. Y is always the height when we're talking about this, or x.
And it's 0.
And it is 0 at the total time. This thing, which is what I'm trying to find. When it goes from here.
Okay, that's y final. Is.
Yeah. Oh, thank you.
That's
Good.
close.
Good. All right. Thanks for sticking with it. Yeah, there you go. Thanks for sticking with the question. Now you clarified it for a lot of people. Good job. So yeah, that's y final equals y initial plus v naught y. So we got 0 plus 0 is 37.t minus 4.9 t squared. This looks ugly, but it's really not, because we've got a nice factoring thing here that we can do. 37.5t minus 4.9t squared. Let's just factor the t out of both sides. We get 37.5 minus 4.9t. Now this makes sense. T is 0, or 0 equals 37.5 minus 4.9t. Now, when t equals 0, that's back here, before Tiger even hit the ball. That's at t equals 0. Now he hits the ball travels, bonk, hits the ground. That's this time over here. So it becomes 4.9t equals 37.5, and so t equals 7.7 seconds. There's another way you could have done it. You could have used, this is alternative way. You could have said, hey, I want to find the time this way because I'm going to find, because I know that the acceleration equals v final minus v initial in the y directions divided by t. You could do that, and you could go, well, I'm going to find v final this way. V final squared equals v naught squared minus 2g times 0, because it went from 0 to 0, y final minus y initial, so it's 0, 0. So that term goes away. We could have said, oh, yeah, so v final y would equal negative 37.5 meters per second. And so you get A, well, you get 9.8. Well, let's just multiply both sides by t. So t equals negative 37.5 minus 37.5 over negative 9.8 meters per second squared. Those are all meters per second. That's another way to do it. That actually might be a little bit easier. Both, it's works out the same either way. That's basically negative 75 over 9.8. Right. Okay. Now, so the t total came out to be 7.7 seconds. So now, if we can get the range, it's pretty easy. The range is going to be 65 meters per second times 7.7 seconds. And that comes out to be almost 501 meters. Okay? Nobody's ever hit a golf ball that far. Unless it was a Super Bowl or something, they whacked it. So this isn't very real world too much. Okay, and let's figure out what the height would be. The height isn't too hard to find. I'm going to do the height problem over here. I'm going to find h. Now, one way to find h, since we already know that t total is 7.7 seconds, I can take 7.7 and divide it by 2 and say, okay, well, h is going to, and then 7.7 divided by 2 gives me the time that it took for it to get up to here. And that's 3.85 seconds. One way to do that, then, is to go, all right, well, I've got 3.85 seconds. Then I'll find y. Just the y at 3.85 would equal 0 plus 37.5 times 3.85 minus 4.9 times 3.85 squared. That's one way to find the maximum height. The other way to find h is to do this. To go, okay, what's VF at h in the y direction? When we get to h, what's the final velocity in the y direction at the maximum height h? 0. 0. Okay, so that's 0. And you could do this. You could say 0 squared equals v naught y squared plus, minus 2g times h minus 0. Final minus initial height. And so h is equal to, you got 2gh equals v naught y squared. And so h is equal to v naught y squared over 2g. So there's a handy instant formula if you want to scribble that down and bring it with you on your cheat sheet next Tuesday. Because I'm going to ask you what the maximum height is. There's one way to find it. And if you compute these two, they'll be the same. I already did it with your compadres at the 2:30 class, and it came out to be the same. I was so thrilled because I hadn't double checked it. All right. So there's projectiles. Everything. Yes?
I don't know what you did for the top y. Like where you got negative 4.9 times 3.85 squared. I'm lost there.
Okay. All right. Here we go. In other words, to find any height, going back to what Mr. Rash said earlier, okay, to find any height then, any height is y equals y naught plus v naught t plus 1/2 at squared. That's the initial, that's the raw formula, okay? And basically it's a derivation from calculus based on the rate of change, okay? All right, starting with acceleration, which is constant. Take the integral of acceleration, you get velocity. Then you take the integral of velocity and you get the distance. And so, which we don't derive, so we don't do calculus here. So I just said, there you go. All right, now, so at any time, to find, if I know the time, give me, this is a function of time. So the height is a function of time. So give me, if I know the time, if I know this, and the acceleration, I know the time, then at any time I can find the height. If I got to know the time though. That's what I did. And so when I plug this in, I get y equals, the initial height was 0, plus this 37.5, which was my velocity in the y direction, times the time, which I figured out was 3.85 seconds, minus, I'm going to factor out, because this is a negative acceleration, so I'm going to factor it out, make that negative, 1/2 9.8 times 3.85 squared. Good question. So this height is a function of time. And all you got to do is plug in these numbers, and I can't remember how high it went. I think it came out to be 8.5 meters. Yes?
AT squared or GT squared?
Well, A is what?
Acceleration.
Acceleration. What's my acceleration?
Maybe not.
There you go.
So it would be A naught. Okay, so.
They're interchangeable.
Okay.
A and G in the Y thing for free fall and for projective. So far, all you know is in AY is equal to negative 9.8 meters per second squared. That's good old gravity. And so that's why I stuck in here for A. But I moved the negative out here and replaced the plus sign with a negative. Little algebra trick. Good question.
How do you get rid of that front part? Because you just have negative 4.9 times 3.85 squared.
No, he just wrote it underneath.
Because you're in the coordinate space. Oh, okay. Well, that's what I was confused. I just saw the.
This is all one thing.
Okay, I just saw the front part and went, I don't.
Oh, yeah. No, this didn't magically disappear. Here it is all written out.
Okay, that makes sense.
All right, good. No, that's fine. Yes?
On the second one, what's the h minus 0, or where'd the 0 come from then?
Right here?
No, on the very right.
Right here, that's the initial height.
Okay.
Because remember, when you use this formula over here from chapter 2, VF squared equals V naught squared plus 2AX or Y. In this case, again, A is negative 9.8, so we do it this way. We've got VF squared equals V naught squared. I got to be careful. It's actually not Y. It's Y final minus Y initial. Okay? So for us here, it's minus 2G times Y final was H minus 0. That's where I got that. Squared. There we go. All right. Let's get our quiz hats on. 4 questions. I think I'm only going to quiz you on 4 questions, and we've talked about all of them. Okay? So shouldn't be any surprises. We'll turn back on the projector. And by the way, while the projector's warming up here, tutors. Two of our tutors are back there. All right. For 210, Tuesday or Monday through Thursday from 10 to 10:50. Might even be through Friday. So it's Monday through Friday. And for us, it's Tuesday and Thursday nights from 7 to 7:50. And that's my boy Song does that one. Okay? And pretty much, if you go down to Flersham Hall between 10 and 3, room 259, there will be an episode of Big Bang Theory. No, there will be, you can go in there and they will help you. Those are physics students. They understand 210 and 220. They may not understand the physics that they're taking right now, but they understand this one. All right? Okay? So, and there's engineering students in there that would be more than happy to help you. And if you want to pay for a tutor, if you want private tutoring, I'll take your name and I'll give it to the Society of Physics Students. I'm sure there's some people there that would do that too. If the price is right. A pizza 51 or something. No, I don't know. It's probably a little more than that maybe. I don't know. All right, let's put down the screen. Let's turn off the lights. And let's do a quiz. 4 questions. I tried to transfer these clicker questions using my iMac this morning at home. I kind of played hooky from school until about 11:30 today. I didn't. Come in. That kind of reminds me of a cartoon, a little newspaper cartoon I read about a kid who told somebody, his dad or something, you know, he was working on being a college professor, and his dad said, well, what are you doing to do that? He said, I'm just working 1 day a week. Anyway, so, all right, here we go. Oh, I started from the beginning. So these slides didn't transfer very well, but I think you can make it out pretty good. It says dropping the ball. From the same height and at the same time, one ball is dropped and another ball is fired horizontally. Which one will hit the ground first? So we got the same height, throw one, drop one. Which one's going to hit first? The dropped ball, the fired ball, they both hit at the same time. It depends on how hard the ball was fired. It depends on the initial height. We got that one? Okay. All right. We'll see if you got that right or not. Okay, moving on. In the previous problem, which has the I'm going to make you think about this one. Which has the greater velocity at ground level when they hit? Which one's going to have the greater velocity when they actually hit? Think about the components of velocity. The dropped ball, the fired ball, neither. They both have the same, which is where they want you to go. And it depends on how hard the ball was thrown. Actually, I mean, if you didn't throw the ball at all, they'd hit the same time, so their velocity would be the same. Okay, so what is the answer to that one? What? C or B? How many think it's B? Why? Colin, why? You're on the spot. Millions are watching too. All 33 views I got last time.
The x component of velocity.
Aha! You've got an x component of the velocity. You don't have an x component when you just drop it. So when you got that vx squared plus vy squared, so it makes it a little bit greater. So scratch out your C and put B real quick. One of these days you're going to take a legitimate quiz, but I'd rather you learn this stuff. I'd rather you show up and learn than get dinged for not knowing. All right, here we go. Okay. Now this one's kind of screwy. Which question is this? 3? All right. It says a battleship simultaneously fires 2 shells. Of course, all math and sciences for military power. Who gets all the funding? The military. All right. But anyway, I think we should start using math and science for good things. That's why all you guys are going to be future doctors and stuff. Anyway, a battleship simultaneously fires 2 shells at 2 enemy submarines. The shells are launched with the same initial velocity. 1 ping only. But anyway, if the shells follow the trajectory shown, which submarine gets hit first? C, A, B, or C? C, both at the same time. Now remember, the time that it's in the air is dependent upon what only? The height. The height. So, which one's going to be in the air longer? The blue guy or the yellow guy? And they're fired at the same velocity, just at very different angles. So which one's going to be in the air longer? Okay, I think we kind of reasoned through that one. Dropping the ball, a projectile is launched from the ground at an angle of 30 degrees. At what point in its trajectory does it have the least amount of speed? It's always got a speed, right? Because we launched it at 30 degrees, so it's always got an x component. But where is it going to be traveling the slowest, the least amount of speed? Okay. We'll stop there. All right. You've been a wonderful audience, as usual. And I'll take your scribblings there. And you all may go. And okay, on Thursday, we will start Chapter 4 because you will be tested over the first little part of Chapter 4, which is basically Newton's 3 laws of motion, which you learned in 6th grade. You did. Don't look at me crazy, Brian. You did. You learned them. I swear. All right. What? That's true. But you've all heard an object in motion will remain in motion unless acted upon by an outside force. Thank you, Amanda.